6.7 Reading Graphs. Don't forget to put the date, don't forget to put your name, and also this should be a number 1 if it hasn't already been changed on your notes. Before we go into reading graphs, we're going to be using 2 words quite a bit in the next few minutes: interpolation and extrapolation. So interpolation is reading information between data points. And extrapolation is reading information beyond data points. Now the way that I remember it is in means inside the points, and extra means, or the extras in extrapolation, which for me is like outside. So if you're having difficulties kind of visualizing it, so if this right here is my line and I have a data point here, I have a data point here. Interpolation is interpreting the graph here. So say I kind of extended the graph to here. This point right here I would get by extrapolation. So let's go into some examples. Jenna borrows money from her parents for a school trip. She repays the loan by making regular weekly payments. What a responsible kid. Love Jenna. The graph shows how the money is repaid over time. The data are discrete. Okay, that means that there are specific points. We don't connect the lines because the payments are made every week. So just from looking at this graph, let's figure out what we can assume. So how much money did Jenna originally borrow? Well, the way I would find that is I would go back to the beginning of time. Well, not exactly the beginning of time, but the beginning of the time of this loan. And I would say, okay, at time 0, so at 0 weeks, we have $200. How much money does she still owe after 3 weeks? So then I would go into my time in weeks. Here's 3. And I would go up here. And I would see, it is between 120 and 160. So that would be 240. Sorry, 140, not 240. And how many weeks will it take Jenna to repay 1/2 of the money she borrowed? So that means that she will have paid $100. Because if she originally borrowed $200, half the money will be $100. So I find 100 on the money owed. And it's right here. I go down. And it would take her 5 weeks. Reading graphs can be easy if all of the data is contained within the graph. But what happens when you need to extrapolate? What happens when the data falls outside of the graph? So here we go, Maya. What a go-getter. So Maya jogs on a running track. This graph shows how far she jogs in 10 minutes. Assume Maya continues to jog at the average speed. So let's use the graph and predict how long it will take Maya to jog 200 meters. Okay, so I see my distance here only goes up to 1200 and my time only goes to 10 minutes. So that means that I need to either like physically extend it or use the information that we have in this graph to be able to make those assumptions. Predict how far Maya will jog in 14 minutes. And here's the thing, we are making assumptions left, right, and center about Maya's jogging. Let's actually begin with the assumptions first, and then it will be a little bit more clear what we need to do. So with this graph, it says right here, assume that Maya continues to jog at the same average speed. So what assumptions are we making? We're assuming that she, or Maya, let's be more specific. That's how I spell my friend Maya's name. M-A-Y. Hey, that's how you spell this Maya's name. So Maya, we assume that she can run indefinitely. Okay, so indefinitely means forever or forever at the same speed. We assume that she can run for 20 minutes. So this graph only says that she can run up to 10 because that's all the data that's been collected. So predict how long it will take Maya to jog 2,000 meters. So if we're assuming that she continues to jog at the same speed, what I'm going to do is see how long it takes her to jog 1,000 meters and then multiply it by 2. So if I go here and I find my 1,000 meters, see where it hits the line? I'm going to go down like this. So I'm saying about 8.5 minutes equals 1,000 meters. So that means if I double the distance, I will double my time. So approximately 17 minutes equals 2,000 meters. Let's use the same technique to predict how far she will jog in 14 minutes. Half of 14 minutes is 7, and we have that right here. So 7 minutes, see where it hits? It's right there, and now I'm going to go across like this. So I'm going to say 850 meters in 7 minutes. So that means that in double the amount of time, so in 14 minutes, we are going to go 1,700 meters. Now again, we're assuming that she can run indefinitely, which means forever, at the same speed. We don't actually know if she can jog for 200 meters, sorry, 2,000 meters, or if she can jog for 17 minutes or 14 minutes. We just know that she can certainly jog for 10. So we're going to move on to an example that is a little bit more abstract. The first two had definite contexts, real life context, but now we're going to move on to something a little bit more abstract. Just looking at a graph, we don't know what x is, we don't know what y is, but we're going to use the graph of a linear relation and we're going to determine different values. So determine the value of x when y equals 3. When x equals, when y equals 3, interesting. We notice here that it will be behind the graph. So I'm going to notice the slope. I know that I'm going to the left 3 for every 1 down, and that's true throughout. Left 3, 1 down. Left 3, 1 down. Left 3, 1 down. So I'm right here at 4. So if I would go left 3, so if I would go 1, 2, 3, so this is -3, this is -4, and this one will be -5, and this one will be -6. Because I'm using what I know, which is 3 to the left for every 1 down. Now I want to get to 3, and I know that 4 is right here. So I'm going to say, okay, so this is -3, -4, -5, and -6. So I know that when y is 3, my x is going to be -6. What I've done here is extrapolated. And I've extrapolated using the slope. So when we talk about slope, we're talking about how steep that line is. Next year, you will be dealing with slope a lot more, but this year we just begin to have a feel for it. This one is maybe a little bit easier. Determine the value of y when x equals 5. So I have an x equaling 5 here, and I go up, and I see that it hits. And so if over 3 x's I'm going up 1, that means for every 1 x I'm just going up a third, and another third, and 3/3. So I go up 1. So I can be actually a little bit more specific because I know that the slope is constant. So I'm going to say, okay, well, I know that this right here, at 3, I'm at 6. At 4, I'm 6 1/3. And at 5, I'm at 6 2/3. So then y equals 6 2/3. Or we can express it as a decimal. I'm fine with that. Y equals 6.6 repeating. Or if we wanted to have it in the rounded, we can say y equals 6.67. This is probably the most comfortable answer for you. I hope that you're okay with that repeating over top. So in summary, we can use graphs to predict data we have not collected. Interpolation between data points. And extrapolation outside of data points.